Hmm. A lens is just an object that's made of some kind of material. Could be glass, or it could be any number of other things, like your glasses are made of glass, if you have glasses. But they're made of some kind of material that takes advantage of refraction to focus light and to form images. There are two kinds of lenses. A converging lens is so called because it brings light rays together. So a converging lens, the standard converging lens, has this sort of double convex surface shape, and then light rays coming in that hit the lens, when they go into the lens, they bend toward the normal, and so they bend downward, and then when they are exiting the lens, going back into the air, they bend away from the normal, and so they wind up bending inward. And so these light rays wind up being focused, and they, as it turns out, they come to a focus in a single point, which is the focal point of the lens. It's called converging because it brings those light rays together. A diverging lens, as you might guess, does just the opposite. Diverging lens, the most common example being a lens that has a doubly concave surface. It spreads the light rays apart. So you've got a light ray coming in, goes into the glass and bends toward the normal. Well, the normal's here, so it bends up, and then here it bends away from the normal, so it bends further up, and it diverges. Goes through the middle, nothing really happens. Over here, it'll bend away more. And if you project these rays backward, and if you draw them well and project them backward, then they also come to focus at a single point, the focal point. And these are the focal points of a lens, just like we had focal points for mirrors. Converging lens, the most typical kind is a double convex lens. Each of these surfaces is convex. And for diverging lens, the most common is this double concave sort of lens. So that's what lenses do. If you've ever either done this or heard of someone holding up a magnifying glass to fry an ant, that's taking these sun rays, the rays of sunlight that are basically, parallel, and focusing them at a single point. And when you do that, there's a lot more heat energy going on, and so you can, fry ants and stuff. Yeah. So as I said, they both have these focal points. Now, in a lot of ways, a convex lens acts sort of like a concave mirror, and a concave lens acts kind of like a convex mirror. And we'll see that in terms of the types of images they form, but for now just note, for a convex lens, the light rays actually converge at a point, just as they did for a concave mirror. Now for the mirror, the point was on the other side of the lens, but the light rays actually converge there. A concave lens, the light rays don't actually converge, but the way they're bent, they appear to be emanating from a source, over here, and a convex mirror did a similar thing. For lenses, we can use ray tracing, much like we did for for mirrors, so it looks a little bit differently. First off, we can draw our P-ray, which is the same as it was for a mirror. We draw it horizontally, and then for a mirror, it bounced back, toward the focus, whereas for a lens, it will bend inward toward the focus. That is how we make our P-ray. We also have the F-ray, which will pass through the focal point on the same side of the lens. Now you notice I've drawn I should probably have said this first. Notice I've drawn two focal points, and that's because if you have rays coming in from this side, then they'll focus here. If you have rays coming from this side, they'll focus here. So there's a focal point on either side of the lens. So our f-ray passes through the focal point that's on the same side of the lens, and then it hits our lens and comes off straight, horizontally on the other side. And then we have our third ray, which for lenses is called the M ray, and M stands for middle, and that middle, it just passes through the middle of the lens, and for an ideal lens, it will not bend at all. And you can see, well, my drawing isn't perfect, but they basically all converge right there, means that our image will be formed out over here. So for an object beyond the focal point, it's going to form an image that is inverted. And actually, it won't always be, in this case, it appears like it's about the same size as the original object, and that happened to work out because it's about twice the focal length away. It could be enlarged or it could be reduced depending on how far out that ray is. All right. Now let's look at another drawing. What happens if our object is between our focal point and our lens? We can, do our ray tracing. We can make our P ray, which is horizontal. Again, it goes into the lens and bends toward our focus. All right. We can make our F ray, and our F ray, when it's inside the focus, we draw our F ray a little bit differently. We draw it so that it's heading toward the focus on the other side, and it bounces off straight. Okay. We don't bother with the F ray here because it just gets confusing. But we can draw our M ray, which would look like this. You notice in this case these are getting further apart, and so we project them backward. And we can see that if we project them backward, they intersect back here, and our image is formed behind the original object. And if we drew it's kind of, sometimes it could be confusing because it might be outside the lens like I drew, but if we draw the F ray, so it would hit the lens here and then bend, hit the lens about here and then bend straight if our lens extended that far, and if we project that backward, it'll converge to the same point as well. It's just the lens isn't actually there. So, so that may just be confusing. Anyway, but the image is formed over here, and this image is enlarged, it's upright, and it is virtual. Virtual, enlarged, and upright. And this is the case for an image formed by an object between the focal length and the lens. Now for this object beyond the focal length, our image is inverted, and it is a real image. The light rays do actually converge. And it could be reduced or enlarged, depending on where it's at. All right, let's do one more. Let's do the concave lens, the diverging lens. So let's say, for the diverging lens, it always forms the same kind of image, regardless of where the object is in relation to the focal length. So we make our focal length. Here's the middle of our lens, and then about over here would be our other focus. All right, and we'll just draw our arrow here, wherever. Doesn't much matter. All right. Now, and we can draw our P ray. P ray goes off horizontally, And then in the middle of the lens, it diverges, but it diverges so that it will project back to the focal point. Alright, we can draw our M ray that passes right through the middle. And then the F ray, for the diverging lens, you draw it heading toward the focus on the other side. But then when it hits the middle of the mirror, it comes off straight. We'll go this way, and we can project that back. And we can see all of those connect at this point right here, and so our image is formed. Aquí. That's here in Spanish. And so our image there is upright. It's a virtual image. The light rays don't actually converge there. And it is reduced in size. And this will always be the case for a diverging lens, regardless of where the object is placed. Whereas for a converging lens, it could be, depending on where the object is, it could be virtual or real, it could be inverted or upright, it could be enlarged or reduced. So those are our ray tracings for our different kinds of lenses. Yes, and in your book, on page 917, there's a summary of the different types of images formed, much like the summary for our lenses. If you compare, not 917, 930. 917 was the summary for mirrors. And if you compare those two, then you can see the parallels between convex lens and concave mirror versus concave lens and convex mirror. So this converging or convex lens can form real or virtual images, can form inverted or upright images, it can form enlarged or reduced images based on where the object is, in the same way a concave mirror can do so. And they all parallel. If the object is between the focus and the lens, it forms a virtual, enlarged, and upright image, and that's the same for a concave mirror. And the same parallel exists between the concave lens and the convex mirror.